Look at a standard broad gauge track. You see the rails, the overhead lines, and the signal post. This is the baseline environment of legacy railway operations. A conventional signal post strictly provides information. It relies entirely on a human operator to observe a red light, interpret its meaning, and physically actuate the brakes. This creates a severe operational vulnerability. If a driver misses that visual cue due to weather, fatigue, or distraction, the train proceeds. In railway operations, this is a signal passed at danger, or SPAD. A heavy-haul freight or passenger train carries massive kinetic energy. By the time a human operator realizes they have passed a danger signal, their physical reaction time and the train's mechanical braking distance are often insufficient to prevent a collision. As long as the execution of braking is decoupled from the information provided by the signal, human error remains an unmitigated variable in train safety. This risk compounds in high-density networks, where complex intersecting tracks and overhead electrification create a high-stakes environment for every operational decision. To address this, Indian Railways is deploying Kavach, an indigenous automatic train protection system. Kavach removes the reliance on passive observation. It calculates the safe operating envelope of the train in real time and enforces active mechanical intervention if the driver fails to respond to a danger signal. Standard block signaling offers discrete point-to-point information. In contrast, Kavach projects a continuous moving mesh over the train, constantly validating the authorized distance. East Coast Railway recently secured approval to deploy Kavach across 631 route kilometers at an estimated 270 crore rupees. For assistant mechanical engineers, this capital investment represents a structural change in rolling stock maintenance. Future maintenance cycles must account for the complex onboard equipment that now dictates train behavior. Kavach's innovation lies in its ability to bridge the gap between trackside data and autonomous mechanical actuation. Inside the locomotive cab, the digital display interface is where the data ingestion process begins. The Kavach safety chain operates through 4 rigid steps. Phase 1 is signal detection. As the locomotive moves, RFID tags mounted between the rails pulse absolute location and signaling data upward to receivers mounted on the locomotive's underframe. This data feeds Step 2, onboard processing. Inside the onboard computer, raw signaling data is converted into a dynamic speed versus distance plotted curve. The system continuously calculates the train's current speed and braking distance. If the trajectory of the train reaches the red danger limit, the logic triggers an intervention. This initiates Step 3, the driver warning. The system identifies that a signal passed at danger or an overspeeding event is imminent based on the calculated physics of the train. Before taking full control, the system attempts to alert the human operator, using auditory warnings and visual cues on the loco display to demand immediate manual braking. The electronic layer generates a digital simulation of the physical environment, but these calculations require mechanical compliance to actually stop the train. If the driver ignores the warnings, the system moves to Step 4, automatic brake application. To physically halt the train, Kavach bypasses the digital displays and interfaces directly with the pneumatic twin-pipe air brake system running along the underside of an LHB coach. The first parameter is the feed pipe, which maintains a static pressure of 6 kilograms per square centimeter. The second parameter is the brake pipe, which is charged to a static 5 kilograms per square centimeter. When Kavach commands a stop, its control unit electronically opens a venting valve on the brake pipeline. This creates a controlled pressure drop, reducing the brake pipe pressure from 5 down to 3.5 kilograms per square centimeter, while the feed pipe remains at 6. This pressure differential physically triggers the distributor valve on every coach in the formation. The distributor valve routes air from the auxiliary reservoir directly into the brake cylinders. The cylinders actuate the brake rigging on the Fiat bogie, forcing brake pads to clamp onto the axle-mounted discs with intense mechanical force. This entire sequence is executed independently of human physical input. During this sudden autonomous braking, AAR Type H center buffer couplers must manage the intense draft and buffering forces generated as the train's momentum is rapidly shed. Kavach functions by integrating algorithmic logic into the mechanical realities of heavy-haul pneumatic systems. We move from the active line to the towing depot, where the physical toll of high-speed operations is managed. While Kavach prevents collisions, sustaining 160 km/h operations requires a new level of mechanical reliability across the fleet. Frequent autonomous braking events increase the operational stress on wheel sets, leading to accelerated wear. For an LHB coach, a new wheel has a standard diameter of 915 mm. Through use and high-friction braking, the steel wears down to its condemning limit of 845 mm. Waiting for rigid overhaul intervals to discover this wear is no longer viable for high-speed reliability. Workshops are now using AI-based defect detection. Trackside cameras capture high-speed images of rolling stock in transit, analyzing them for defects in real time. The AI identifies flat spots, spalling, and thermal damage caused by braking forces, allowing for immediate corrective action. This transitions wheel maintenance from arbitrary schedules to interventions based on the actual condition of the asset. Consider a diagnostic scenario. A coach arrives post-overhaul, exhibiting low brake power and frequent compressor operation. The most likely cause is an air leak within the brake cylinder itself. The diagnostic protocol requires inspecting seals, the cylinder bore, and every pneumatic joint before authorizing a replacement. Engineering is shifting away from manual registers towards continuous asset condition monitoring. This is the digital twin, a live, virtual replica of the physical coach fed continuously by sensor data. The digital twin monitors specific components, such as the secondary air springs on a Fiat bogie, and predicts wear before pressure drops occur. Workshop supervisors use this data to organize predictive maintenance, maximizing fleet availability. These digital diagnostics support the mechanical reliability required by the Kavach ATP system. Mastering this future requires engineers to fluently translate between digital software frameworks and exact pneumatic realities.